Welcome to The Explainer. All right, today we're going to dive deep into one of the oldest and, honestly, one of the most powerful sources of renewable energy out there, hydroelectric power. We'll get into everything from the massive engineering behind the dams to the basic physics of how you turn water into electricity.
Okay, so here's what we've got on tap. We're going to start with the absolute core principle of how you harness water's power. Then, we'll walk through the anatomy of a hydropower plant. You'll also hear them called Hydel plants. After that, we'll check out the different types, weigh the good against the bad, and finally, take a look at where this energy source is headed in the future.
All right, first things first. Before we jump into all the complex machinery and these incredible, massive structures, we've got to get a handle on the simple and, honestly, kind of elegant idea that makes this whole thing work.
At its very heart, hydroelectricity is just a beautiful chain of energy conversions. It all starts with a ton of water being held way up high. That's your stored potential energy. Then, you let that water fall. As it falls, that potential energy gets converted into the kinetic energy of motion. That motion is then used to spin a turbine, creating mechanical energy, which, finally, drives a generator to make the electrical energy we all use. It's just a fantastic, efficient process.
Okay, so you've got the principle down, but how do you actually turn that into a real, full-scale power plant? Let's walk through the essential components that make this happen on a massive scale.
This diagram right here, it shows you the entire system from start to finish. Just follow the water's path. It starts up there in the reservoir, flows down that really steep pipe called the penstock, rushes into the powerhouse, and then exits out into what's called the tail race. We're about to break down every single one of these pieces. The dam. This is the big one, the cornerstone of the whole operation. Its main job is to block the river and create a huge, deep reservoir. This does two really important things. One, it gives you a steady supply of water. But even more importantly, it creates what we engineers call head. That's the vertical distance the water is going to fall. That H value is absolutely critical in the power equation. Simply put, the greater the head, the more potential energy you have to work with.
So, if the dam is the cornerstone, think of the penstock as the main artery of the power plant. It's this absolutely massive, super reinforced pipe that channels all that stored water and just funnels it down towards the turbines. As that water barrels down, its potential energy is rapidly converted into kinetic energy, building up immense pressure and velocity by the time it hits the bottom. And here we are at the powerhouse. This is where the final, crucial conversion happens. That high-pressure water from the penstock slams into the blades of the turbine. That's our prime mover, and gets it spinning at an incredibly high speed. That turbine is connected directly to a generator, and voila, the spinning mechanical motion is converted into electrical energy. You know, you might think that once the water spins the turbine, its job is done. But nope, it's still moving, it still has kinetic energy. And that's where the draft tube comes in. It's a really clever bit of engineering. See how the pipe gradually gets wider? That shape actually slows the water down, creating a suction effect that helps pull even more water through the turbine. It's all about squeezing every last bit of efficiency out of the system.
The spillway is the dam's absolutely essential safety valve. I mean, think about it. During huge rainstorms or a massive snowmelt, the reservoir level can get dangerously high. The spillway gives all that excess water a safe, controlled path to get downstream. Without it, water could just pour over the top of the dam, which could lead to a catastrophic failure. So this thing is non-negotiable.
Now, it's super important to remember that not all hydro plants are created equal. Their design really depends on the local geography and, crucially, how they manage their water supply. So let's look at the main ways we classify them.
Okay, this is a key distinction for any energy engineer: storage versus pondage. It's all about the time scale. Storage refers to those massive reservoirs that can hold enough water to run the plant for a whole year, even through a dry season. Pondage, on the other hand, is all about the short game. It's a smaller, temporary storage used to manage the daily ups and downs of power demand. You know, cranking up the power when everyone gets home from work and then dialing it back in the middle of the night.
And here you can see two totally different philosophies at work. And it all comes back to that head we talked about. On one side, you've got a low-head plant, often called a run-of-river plant. It just diverts some of the river's natural flow. But on the other side, a medium-head plant uses a big old dam to create a really significant height difference. That means way more pressure, way more power, and a lot more control over when you generate.
All right, check this out, because this is probably one of the coolest and most important types of hydropower today: pump storage. This isn't just about making power, it's about storing it. Think of it like a giant rechargeable water battery.
When electricity is cheap and nobody's using it, like in the middle of the night, the plant uses grid power to pump water from a lower reservoir back up to an upper one. Then, when demand is high and electricity is expensive, they just release that water back down to generate power when it's needed most. It's a total game changer for grid stability.
But of course, there's no such thing as a free lunch, right? Like any major energy source, hydroelectric power is a story of trade-offs. It has some truly incredible benefits, but it also comes with some very significant challenges. Let's take a balanced look. This table really lays it all out. On the plus side, the fuel, water, is totally free. The plants can last for over a century, and they produce clean, reliable power with no air pollution. That's huge. But then you look at the other column. The upfront cost to build one is astronomical. They take forever to construct, and the environmental impact? Well, flooding huge areas of land and altering entire river ecosystems is a really big deal. So, we've walked through the engineering, the different types, and the major trade-offs. What's the bottom line here? What are the big picture takeaways for the future of hydroelectric power? The key takeaway is that it's all a balancing act. Hydropower is a proven, powerful, and clean technology, but its immense footprint means every new project requires a very careful calculation of costs and benefits. And as we integrate more intermittent renewables like wind and solar, the role of pumped storage hydro as a massive battery for the grid is becoming absolutely critical.
And that's really the question we'll leave you with. Hydropower is a double-edged sword. It's a source of immense clean energy, but one that reshapes landscapes and ecosystems forever. Finding the right balance will be one of the key challenges for energy engineers and policymakers for decades to come. Thanks for joining us.